Welcome to Lesson 1 from Chapter 7, Trigonometry and Modelling. This is from Year 2 Pure Maths, and today we're going to look at compound angle formulae, which are actually trigonometric identities. So yes, there's more identities to be playing with in this course, and these identities are given to you in the formula booklet, so there is no need to learn them off by heart, but as you'll know from previous experience, if you do know them off by heart, they're more tangible, they're at your fingertips, and it makes the questions easier to answer. Okay, so there's going to be a little bit of revision of CAST and all that work you did in year 1 and perhaps prior to year 1, and obviously your algebra skills will come in handy as well. So without further ado, please pause the video, attempt the 4 warm-up questions, and we will go through the solutions together. Okay, and let's have a look at the solution to question 1. So in this question, we have sine A as a negative value, -8/17, and we're told explicitly in the question that this angle is reflex, and more specifically, it's between 180 and 270 degrees. So we know exactly which quadrant it's in, so that could be handy. And because we have the value of sine, we can deduce very easily the values of cosine and tan. And what we will do is we'll assume, first of all, that A is an acute angle. I'm just going to make a note of that because that's an important point. So first, assume A is acute, or let A be acute. Now, if we do that, we can dispense with the negative sign. We're essentially finding a principal angle. So therefore, sine of A is just going to be 8/17. Okay. If it's an acute angle, the sign of the angle cannot be negative, because if it's in the first quadrant between 0 and 90 degrees, all sine, cosine, and tan are positive, as you know from the CAST diagram. What I'm going to do now is I'm going to draw a right angle triangle. Okay, and then we can simply find out what the cosine and tan are going to be. So let's have a look at the information we've got here. So remember, these are trig ratios, they're proportions, and we're comparing the opposite side, which I'm going to put here, to the hypotenuse, which is obviously here. Okay, and I'm just going to label the angle, which is what I should have done first of all. So this is going to be my angle A here. Okay, just to seal the fact that the opposite side is, of course, that one I've just labeled as a pink blob. So if that's the situation, if we just put the numbers in now, so we know that the opposite side would be 8, perhaps, and the hypotenuse might be 17. So wouldn't it be great if we could find out what the adjacent side was, and then we can work out the cosine and the tan? Well, we can. I mean, I've got my calculator here if need be, but we can use a bit of Pythagoras' theorem here. So just state what I'm doing. So by Pythagoras' theorem, we're going to have the adjacent side is just going to be the square root of 17 squared, which is the hypotenuse, subtract 8 squared. It's the difference between the hypotenuse squared and one of the shorter sides squared, which in this case is the opposite. So if we plug those numbers into the calculator, so we take the square root of 17 squared, you might know the answer to this already, but we'll just do it anyway. Subtract 8 squared, just come out of that square root. Oh, and we get 15. It's one of those fantastic Pythagorean triples that we really like. Makes life so much nicer. So this is equal to 15. Okay, so we can now add that to our diagram. So that side there is worth 15. And this means we can write down some more information. Okay, so what I'm going to do, I'm just going to partition the board. So for acute A, just carrying on with this, we know sine A already, that was given to us, but we also can tell us, we can also can state that cos A is 15/17, and tan A. Now, we haven't answered the question yet, but we'll get onto that in a second. But in this case, for acute A, tan A would be the opposite over the adjacent, which is, of course, 8/15. Okay. Now, how do we answer the question? Well, we now need to use the cast diagram because, of course, we are cheating a bit here. A is not acute. It is a reflex angle. And in fact, it's in the third quadrant. So let's draw a cast diagram now. So for A to be between 180 and 270 degrees, this is answering the question now. Draw a little cast diagram here. Okay. The quadrant we are interested in between 180 and 270 is of course the tan quadrant, okay, which means that, of course, tan only, oops, didn't want to do that, tan only is positive. So that answers our question for us. So sine is clearly negative because we're told that in the question here, aren't we? We can see now the reason why sine is negative because we're in the tan quadrant. So to answer the question, we can just write down our answers, which we'll do now. So we'll have A, the cosine has to be negative. So that's going to be negative 15/17. And for part B, the tan is positive. So we can keep it as it is. So that's going to be 8/15. So it's a nice little use of the right angle triangle angle reasoning, not angle reasoning, but SOHCAHTOA, I should say, and combining that with the cast diagram to answer these questions. So for part 2, or question 2, we've got this situation where we can see from the cast diagram here that the cosine of negative theta, so as we're going clockwise around the cast diagram, we get this result. Now, you don't need the cast diagram for this. You can see because cosine is symmetrical about the y-axis, the cosine of the negative angle must correspond to the cosine of the positive because of the symmetry. But the cast diagram does the same thing for us. It shows us that the cosine of the negative theta, whatever theta is, if it's an acute angle, because cos is positive here and cos is positive here, that the cosine of theta and the cosine of negative theta must be the same value, which is what's stipulated here. So how does this pan out for sine and for tan? Well, I'll do them in different colors. If we look at sine of theta, now clearly sine of theta is a positive because all trig ratios in that first quadrant are positive. But what about the sine of negative theta? Well, we know that only cosine is positive in this quadrant. Okay. So yes, there would be the same value if we took the absolute value, but because only cosine is positive, that means that the sine value in that quadrant must be negative. So I'm just going to make a note of that. So we know the sine value here is positive, but the sine value here is negative. Now that means you can put them equal to each other, provided you change the sign of one of them. So to answer the first part of the question for sine of negative theta, okay, we can say, all right, sine of negative theta just do that again. Sine of negative theta is almost equal to the sine of theta, but sine is negative in that fourth quadrant, so they can't be the same sign. So we have to change the sign of this one. Okay. Now, it's the same situation for tan. It's only cosine that's positive in that fourth quadrant. I'll say it again, really important, only cosine. So tan behaves in exactly the same way. And again, you'll see this if you sketch the graphs. You'll see that these functions are not symmetrical about the y-axis in the same way that tan is symmetrical. Sorry, I beg your pardon, that cosine is symmetrical. Okay, they have rotational symmetry, but they do not have reflective symmetry. Okay, but I'd leave that as an exercise for you. If you want to explore that a bit further, maybe use some graphing software such as Desmos or GeoGebra. Okay, I hope that makes sense. For question 3 is a slightly unusual question, but you'll find out why later on. You're given 3 angles, 30 degrees, 45 degrees, and 60 degrees. And you have to try and create as many different angles as you can by adding or subtracting them. So presumably that's in pairs, as the pattern suggests. I don't know if there's any more of these. I've written out a few here. So they need to be unique, as in like different. So we've got 120, 15. So we've got 45, 105, 90, 60, and 30 there. The last 3, though, are quite standard angles, aren't they? They have trig values that we've been using for a while, so they should be recognizable. So I'm not sure how useful they will be, but I do want you to be cognizant, there's a good word, of these angles in particular. So 120, 15, 75 there, and 105. All right, as sort of linear combinations of the ones that are suggested, the 30, the 45, and the 60. Okay. And the final question is a disproof by counterexample. Okay. Now this identity is not true, of course. That's why we have to disprove it. But it's a common mistake made by students when we embark on these compound angle formulae. Okay, you can probably see what's happened here. It makes sense because you've spent years expanding brackets to simply take the sine of A as a product, and then sine of B, and add them together like you would when you're expanding brackets like that, which is clearly what this identity implies. Okay, but it's not how it works, and we can show this with a classic counterexample here. Now, it's up to you what angles you choose for A and B. I'll just give you something reasonably straightforward. So let's say let A equal, I think we'll use A as 30 degrees. Okay, and B we can use as 60 because we've got those ready-made angles on the left-hand side over here. Okay. Now, if we sub all this into the identity, I'm going to start with the right-hand side, first of all. I'm going to do them separately. So we have the sine of 30 degrees. So I'm just showing I'm subbing 30 degrees in there. Okay, and then add the sine of 60 degrees. Okay, so if we fill these in, of course, the sine of 30 is, of course, 1/2. So this is going to equal 1/2. And then correspondingly, if the sine of 30 is 1/2, then the sine of 60 must be √3/2. Okay, like that. And then we just have to, oops, sorry about that, √3/2. And if we add them together as a single single value, that'd be 1 plus root 3, which is irrational, of course, over 2. So that's on the right-hand side. Now, for the left-hand side, we can consider that separately. If this identity is true, we should get the same answer, shouldn't we? So this time we're going to add the two angles. I'm going to sub them in and then take the sine of them. So that's going to be 30 degrees added to 60 degrees inside the bracket, like so. Okay, and this is equal to, of course, the sine of 90. And you'll probably know the sine of 90 is not 1 plus root 3 over 2. It's simply 1. So what we've done is we've disproved it. So these are not equal. So we just state, just to finish off, just give myself a bit more room. So therefore the sine of A plus B cannot be identical to the sine of A plus the sine of B. Now notice it's enough to use one case here. All right, it's an identity we are disproving. Identities have to be true for all values of A and B, no matter what you sub in. This always has to hold. And because we found a value of A and a value of B immediately that doesn't work, this identity is broken, so that can't be true. Okay, there may be instances where the sine of A plus B is equal to the sine of A added to the sine of B, but that wouldn't be an identity, that would be an equation, okay, which you could perhaps solve. So that's enough. So we've just one single counterexample, we've got to the result that we needed. Okay, so that concludes the warm-up. Before we continue with the notes, I'm just going to show you the compound angle formulae, which are identities. And you can see them stated here. We're going to look today at the first three. We're not going to touch on the rest of the identities on the screen. Now, this is taken from the Pearson Edexcel formula booklet for A-level maths. And I just want to explain how to use these formulae should you be using them in an exam situation. So you can see here we've got the double sign plus minus, which is repeated here. So for example, if you are going to use a compound angle identity for sine, and what we mean is it's if you want to combine two angles as a sum, such as A plus B, like that, then you can actually write them in the following way. So because that sign repeats, it's in the same order. So if I just write this out, it's going to be sine A cos B. Like I said, because these are the same orientation with the plus and the minus in the same position, if I want to make an addition here, then I have to put an addition there because that's what the identity is telling me to do. So I put an addition there, and then I put in cos A sine B. Now, these are useful because it means that we can separate out the angles A and B using these identities, and you'll see more about that later. Similarly, if I was going to write a subtraction, so sine of A subtract B as a single angle, I would do almost the same thing. Okay, but I would have to write a negative sign separating those two products. So that would be subtract cos A sine B. All right. So those are the two sign identities. We're going to focus mainly on the addition. The negative one here is a special case. And for the cosine one here, notice that if I just highlight this, because this is so important and I don't want you to make a mistake with this. If you notice, we've got the plus and minus orientated the same way, with the plus on top and the negative on the bottom, but these signs are flipped on the right-hand side of the identity. Now, just as an example here, what this means, if I want to work out the cosine, so I'm doing this in red because I think it's really important, of a plus b, notice the plus is on the top here. Okay, that is identical to the cosine of a. I'm just following the identity. You'll see why it's like this later. Cos b, and then if you notice in the middle, we have the negative sign on top. So that corresponds to the positive sign on the left-hand side. So it's going to be subtract sine A, sine B. Notice the subtle differences in these formulae or identities. Okay, and then obviously if we were doing the cosine of A subtract B, the sign in the middle, which is here, would become a positive. All right, so just something to be aware of. And then there's this a similar behavior with the tan one here. So we have the plus will correspond. So the plus will correspond in the numerator between here and here, but notice in the denominator it's reversed. So you would have the tan of A plus B would have 1 subtract tan A tan B in the denominator. Okay, so I hope that's clear. So now we're going to move on to the derivation of these identities, which is going to be very exciting. Okay, so first up, this is task A. This is a task for you. So I would like you to pause the video in a moment when I tell you to, and have a go at this yourself. Now, what we have is we have on the screen, although you can't see, I'm just going to scroll down. We have 4 right-angled triangles, and the labeling will be slightly different. So the description, quite similar to what you would get in maybe in a GCSE question, where you're given all this angle information here and any measurements that you might need. It's all provided for you in that sentence. So you're going to use that information that's presented to you and the diagram, and you're going to find the lengths of the missing sides, in this situation, AC, okay, and CE. Okay, that's the first one. And then notice in the second right angle triangle for part B, you're finding the missing sides FA and EF. So in other words, the 2 shorter sides. And I'll just clear that. And then moving down into part C and D, you're going to be finding the missing sides AB and BC, and the CD and DE for part D. Notice though, it says use your answer. Let's get rid of that, sorry. Use your answer to part A to do this. So use your answer to part A to do this, and same thing here. Okay, so just read the instructions carefully. Okay, and you can pause the video and we'll see what these lengths are. Okay, and they will be in terms of alpha and beta, of course. Okay, so for A, we've got 1 as the hypotenuse, and we want to find AC and CE. So it's a bit of SOHCAHTOA, isn't it? Now then, hopefully this wasn't too much trouble. If I want to find AC and CE, I can label them first as the opposite, as in opposite to the angle labeled beta here. Okay, and this is the adjacent side. Okay, if necessary, you can write out the SOHCAHTOA, which I've obviously told you it's a SOHCAHTOA task up here. So if you want to do that, we could say, all right, for the opposite, the sine of beta is just going to be the opposite over the hypotenuse. The hypotenuse has conveniently been chosen to be 1. So we now know that the opposite side is just going to be sine beta. Okay. All right. Now, that means that the opposite side, which is EC, is sine beta. And if you haven't done so, what I would recommend you do is you label that side. So this is sine beta. Now, again, you've done this before. We've done this in mechanics as well. Without doing any more work, the adjacent side is, of course, going to be cosine beta as well, because we've got a hypotenuse of 1, so there's no scaling. All right, so I'll do that in blue. So this is going to be cosine of beta. Okay, and you can see last year's trig identity is staring at you. You can see the tan of beta is going to be sine over cos. All right, and you can also see that cos squared beta plus sine squared beta is 1 using Pythagoras. Okay, so we're going to do the same thing for part B. We're going to find FA and EF, the two shorter sides. And we again have a hypotenuse of 1 to play with, which is really handy. There it is. So we can just write these down, I think. If you want to use SOHCAHTOA, you can do. So this side is going to be the sine of the angle that's presented here, which is the sum of alpha and beta. Okay, using Greek letters in this question. All right, and then for EF, again, same rules apply. Cosine of alpha plus beta. All right, so I hope that wasn't too tricky. Let's have a look at parts C and D now. All right, now I've just added a sketch from part A here because I can't show it on the screen in all together. So I've just put the sketch there as a reference from what we've just found. Now, probably what I didn't make clear earlier was that all these triangles are linked. So if we see on the sketch from part A that we have here that I've just drawn, that side AC, obviously we have another side AC on the diagram here. So they are they are the same side essentially. They correspond. So the letters and the sides do correspond, and they all fit together in a pattern, which we'll see later, or a greater diagram. So that means that using my answer to part A as it stipulates here is basically telling me that I can label this side AC. Okay, from the work we've already done. So I'm going to do that. I'm going to do that in red. So this side here is cos beta. So if you were wondering where are all the measurements, we can't do anything without at least one measurement. There's your answer. So that side AC corresponds to this diagram here. Okay. Now we're in business. So now we can use our SOHCAHTOA to find out what BC and AB are. All right. Now, if you're not comfortable with this, you can use the SOHCAHTOA rule. All right. So once again, we have the opposite side over here. We have the adjacent side here. Now, if I want to find AB first of all, okay, that's the adjacent side. We're going to be using cosine. So this means that the cosine of alpha is going to equal the adjacent side, which is AB, over the hypotenuse, which is cos of beta. All right, now a little bit of rearranging. We now have that AB is going to be cos alpha, because I'm going to do it in alphabetical order, cos beta, the product of those two. So that's good. So we've got that. And then for the opposite side, which is obviously here, we're going to be using sine. Okay, so I'll do that. So the sine of alpha is going to equal the opposite side, which is BC, divided by the hypotenuse, which is cos beta. And once again, a bit of rearranging. So therefore, BC is going to equal, that equal sign wasn't very good. sine alpha, cos beta, the product of those two. Okay, so we've got some important results here. I'm just going to highlight them, make them look really important. Okay, so we've got lots of information just from a little bit of SOHCAHTOA on 4 right-angle triangles. So we've just got to do part D now. So I'm hoping you're following this okay. Once again, we can use our answer to part A. So I'm going to reuse this sketch in the bottom left. Now this time, you'll notice that the side I've got here is EC, or CE if you like. Now that corresponds to this side here, CE. So I know I'm going to label this one as sine of beta. And if you're wondering what all this is for, you'll find out in a minute. Okay, so we've got sine beta. And once again, we do the same process. Now, without going through the whole thing again, just a little bit of SOHCAHTOA here. So we can use the cosine for CD. So cos of alpha is going to be the adjacent side, which is CD, over the hypotenuse, which is sine beta, like that. And that means that the side CD is simply going to be cos alpha sine beta. So I'm doing it Greek alphabetical order, alpha and beta in that order. Okay, so that's good. And now for the opposite side, ED, we're going to use sine again. So sine of alpha is going to equal, or DE, we'll do that in alphabetical order as well, over the hypotenuse, which is sine beta. And we now have our DE in terms of alpha and beta. So that's going to be sine alpha, sine beta. And once again, make those look really important. So we've got CD there. Okay, and we've got DE. So we've got lots of important information, and we're going to use that information in the next part. Okay, now we have task B. This is another task for you guys. What I'd like you to do is use everything you found in task A to label this diagram that's presented to you. Okay, so pause the video and see if you can label the sides based on the information you found in task A. Okay, good. Right, so you've had a go at that. Let's have a look at the solution. All right, so what I've done is I've just summarized all our findings from task A in this summary here, this list. All right, now you have the diagrams in front of you as well, so you have a slightly better idea of what's actually going on. But the idea behind task A was to give you a bit of scaffolding in labeling this diagram. Now, the first place I'd like to start is with part A, as you can see here. Now, we've got some measurements we can add to our diagram. So AE has a length of 1 unit. So I'm going to add that onto the diagram. So there, that's not a diagonal line, but it's a line that cuts from the corner to the opposite side of what looks like a square or a rectangle. We don't quite know yet. Okay, we also have AC, which is cos of beta. So I'm going to put on here. You can see AC. And we also have CE. So it looks like the triangle from part A is this right angle triangle in the center, all right? So which has all its vertices as points on the perimeter of a rectangle. So this also makes this angle here beta, okay? When I say this angle, I'm referring only to this part. All right. Now, what do we do next? Let's move on to part B, and we've got EF and AF. Well, EF, as you can see, it's reversed. It's EF is here, okay, and that's going to be the cosine of alpha plus beta. You'll see why in a second if you haven't seen already. Okay, so this is going to be the cosine of alpha plus beta. Okay, and AF, which is the vertical side on the left, is going to be the sine of alpha plus beta. So I'm going to write this vertically like that. Okay, and can we see why? Well, this is a right angle triangle, and we know that this side here is the opposite side, as is customary because it's the sine of the angle. We've got a hypotenuse of 1 that it shares with the triangle ACE. Then that makes the angle in the corner up here in the top right. This must be the angle alpha plus beta. Okay, and you may have noticed as well that this is actually an alternate angle, alternate to the angle that we were dealing with a few moments ago. Okay, so the angle that subtends BAE. Now that means that if you can see that alternate angle, I'll just get rid of that. That makes the angle at the bottom here, this must be alpha. All right, so that must be angle alpha because we can see from the result up here that this is alpha plus beta. Okay, so this is interesting. So we've got quite a bit of it labeled already. Now, if we move on to the part C list, we've got A, B, and BC we can put in. Now, you'll notice that's the triangle from part C, resting on the bottom. We have the angle already. We know the hypotenuse, which is here, of this angle is cos beta because that hypotenuse is shared with the adjacent side of the triangle ACE. So we can just write those on. We've got those sides already from the SOHCAHTOA work we did earlier. So I know that this side is going to be cos alpha, cos beta. Okay, and the opposite side BC is sine alpha, cos beta. Okay, there's no trickery in this. This is all standard stuff, just standard SOHCAHTOA. It's just the diagram has been chosen in a particular way, okay, to facilitate what I'm going to show you now. And then for the last part, we've got part D, which we've not used. So we've got CD and DE to label. Okay, that's great. So that's going to be the triangle up here in the top right. Okay, so we can just add those sides on. Notice that the hypotenuse of that triangle is the sine beta because it's shared with the side EC on the triangle ACE. So that's good. So we just add those on. So what do we have? So we've got CD is cos alpha sine beta. Okay, and DE is sine alpha sine beta. Right, and we've got everything we wanted, I think, from task A. Now, let's see what's actually going on here. Well, we're asked to write down, in part B of this task, we're asked to write down some identities. Now, we can probably, before we do that formally, let's just have a look at what's going on. Well, we can see, I just use a bit of highlighting here. Because this is a rectangle, as far as we know, it's at least a rectangle because we have the 4 right angles in each corner. Presumably that is a right angle as well. It's forced to be because of the 3 right angles are fixed. What we now know is that these sides must correspond. And what I mean is by these sides is the whole length of this side must be equal to the whole length of this side. So in other words, DF must equal AB. So let's just make a note of that. So we know that AB is equal to DF from the diagram. Okay, so therefore, cos alpha, cos beta must equal cos of alpha plus beta, and then I've just run out of room here, plus sine alpha sine beta. All right. Now that's quite an interesting result, isn't it? Okay. Let's highlight that. That looks like it might be useful. So I hope you can see that, guys, and maybe you've deduced it yourself already. Okay. Let's use the same principle with the other straight sides of this rectangle. So we've got, and what I mean is the vertical side. So we've got AF and BD, they must correspond. Okay, they must be the same length because we have a rectangle. Okay, so AF is equal to BD. So what's AF? Well, AF is sine of alpha plus beta. Okay, and BD, well, it's the sum of BC and CD, isn't it? So this is going to be the sine alpha cos beta added to cos alpha sine beta. Okay, and I think that probably looks familiar from the formula book that you saw not so long ago. So this looks like we've got another result here. Right. Now we're in a position to write down our identities. So for part B, there we have it. Those are our identities. Now I've made them look really important. I suggest you do the same. Get your highlighters out, put them in a box. In fact, let's put a nice border around the box. All right, these are given to you in the formula booklet, but once again, if you can learn them, get used to them, they're at your fingertips and you'll find problem solving much easier. So in the first one, the cos of alpha plus beta, I've just rearranged the result from the diagram. Okay, so I've just made the cos of alpha plus beta the subject there. And the sine of alpha plus beta just kind of fell out of the diagram, didn't it, essentially? Okay, now you'll see in the formula booklet, I've used Greek letters here. You might not like that, I don't know. There'll be a straight swap in most situations. When you see these identities presented, you'll see alpha will usually be A and beta will usually be B. So if you want to swap those out now, you can do in your notes if you don't like the alpha and beta. But these are the bedrock of a lot of other identity proofs that we can now produce. Okay, so we're going to look at some applications of this in the worked examples. Right, so for worked example 1, we have a classic proof, okay, which may be asked under exam conditions. It asks you to use, or tells you to use the results from task B. So we've just completed task B, and we've got two new compound angle identities, and with those as our raw materials, we're asked to show that this identity is true. Okay, now what I would recommend you do at this point is to pause the video and have a go at this yourself. All right, it's a nice exercise and it will get you used to manipulating the identities a little bit. So please pause the video, try this yourself, and then I'll go through the solution with you. All right, okay, so now you've had a go at this, let's see if we can come up with a valid strategy here. So we've got the tan of a plus b, and we have from task B, we've got two identities. So I'm going to write them using a and b now. We're going to dispense with the alpha and beta. So we know that the sine of a plus b is identical to the sine of a cosine of b plus the cosine of a and the sine of b. Notice they alternate, but I've kept the a and the b in the same order. Okay, so that's the first one. And then we also discovered that the cosine of a plus b, which was alpha and beta in task B, is cos a cos b. Now it's a subtraction, subtract sine a sine b. All right, and we have to show, or we have to prove an identity that involves the tan of a plus b. So is there something else in our armory that we can use to show this? Well, yes, there is. We've got information from year one. We know, so I'm going to do this in red. This is important. We know that tan of some angle theta is identical to sine theta over cos theta. Yeah. So therefore, let's put in our new angle now. So tan of a plus b as our angle, so where theta is a plus b, must be the same as the sine of a plus b over the cosine of a plus b. Now, this really does highlight the power of identities. It doesn't matter what the angle is, okay? The angle can be any real number. This thing here, it doesn't matter. We've called theta a plus b, but the identity is still valid because it's true for all values of theta, okay? So I've just made a substitution for theta and a plus b, and we've got an identity that is still valid for tan of a plus b. So what can we do with this? Well, we have identities for sine of a plus b. So I can continue this without doing too many mental gymnastics. I can now say, well, the sine of a plus b is what I've got written up here. So that's just going to go in for the numerator, isn't it? So I'm going to have sine a cos b plus cos a sine b. And I'm not expecting you to be that fluent with these identities just yet. You've only just met them. Okay, and all this is going to be divided by the cosine identity, cos of a plus b, which we can replace with cos a cos b. Okay, subtract sine a sine b. So we've made some progress, haven't we? Okay, we've now got, it doesn't look like it yet, but we're on the way, because we've now eliminated the a plus b using our new identities, and we've now got a's and b's everywhere here, in the same way that on the right hand side on our identity here we have a's and b's. Yes, they've got tans in there, but they are separated. There is no a plus b anymore. So we've done that job. So the question is, how do we create the tan a's and the tan b's that are present in this identity? We've got tan a's and tan b's all over the place. Well, we can go back to our favorite identity here. We know it doesn't matter what theta is, as I've got it here. It can be a plus b, it can be a smiley face. It doesn't matter. It's still valid. So I'm just going to make another note over on the left over here, that if I have tan of a, it's identical to sine a divided by cos A. And I also know that tan of B, whatever B is, must be identical to sine B over cosine B. So the question is now, how do I create those tan A's and tan B's? Well, this is the step. This is the important bit. It looks like to create the tan A, I'm going to have to divide my sine A by cos A. And to create my tan B, I'm going to need to divide my sine B by cos B. So in our identity over on the right-hand side of the screen, okay, which is here, I'm going to have to divide my terms. It's going to have to be everything by cos A and cos B. Now I'm going to do that in two steps. We'll do the cos A first, so you can see what happens. So every term, in order to keep the fraction in the same proportion, we're going to have to divide every term by cos A. Right, so let's do that. So we're going to have sine A cos B. But now I'm going to divide that by cos A. And in the second term in the numerator, I'm going to have cos A sine B divided by cos A. Okay. Now, that's fine, but I've got to maintain this. I've got to do it to every term in the entire fraction. So this is all going to be over cos A cos B divided by cos A. And then subtract sine A sine B all over cos A. So every single term, whether it's a product or not, they're all products, aren't they, of sines and cosines, they all have to be divided by cos A. Now, what does this reveal? Well, let's see what happens. We want to create a tan A. Now, going back to the tan A, that's sine A over cos A here. I've got that in the first term in the numerator. So I've created a tan A there. What I've also done is in the second term, I'm going to cancel out the cos A's here. They're just going to cancel. So I'm just going to be left with sine B there. I've also got cancellation here with the cos A's. Okay. And I've created a tan A there. So that's really good. I'm just going to make a note of what I've got here. So that's really good. So this is just going to be tan A. Okay. This is just going to be tan A. And then these are just going to cancel to 1. So let's see what I'm left with. All right. Now I'm just conscious of space here. So I'm just going to continue this question over here. So I'm going to write the next step over there. So we're going to have, so let's write this out. So once again, I'm just going to write that tan A. That's the new part. So we've got tan A, and that's multiplying cos B plus sine B. And that's going to be all over 1 multiplied by cos B, sorry. Subtract tan A and then sine B. It's one of those proofs where if you remember just a couple of key things and you're confident with your algebra, the whole thing will just sort of reveal itself really nicely, just with a bit of manipulation. Right. Okay. So we've got the tan A's. Now we need to create the tan B's, which are here. Now to create the tan B's, I need to divide everything by cos B. Okay. Because we've already established that tan B is, of course, sine B over cos B. It's the same principle as the tan A, which we saw there. So let's do that. So we're going to divide everything by cos b now. And you could have done this in one step. You could have divided everything by cos a, cos b, but I didn't want to bombard you with cancellation and substitutions in just a couple of steps. It would have been probably too much. All right, so let's do this. So we're going to have tan a cos b plus sine b, and we're going to divide those separately. Well, you could do them all in one, but divide that by cos b and divide that by cos b. And this is, of course, that's the numerator. And in the denominator, we've got cos b subtract tan a sine b, and both of those terms need to be divided by cos b. Like so. So this is quite an example to start off with, isn't it? Now let's have a look what's happening now. Hopefully this is going to give us the result we want. We have created, no, that's wrong, sorry. We have cancelled out the cos b's here, which is great. And we've cancelled out the cos b's here. So these are just going to become 1. And notice that we've got sine b over cos b here. That's going to be tan b. And we've got sine b over cos b here. So that's also going to be tan b. So there we have it. I think that's enough now to say that we've got our result. That's tan b. That's tan b. And all we've done is taken the identity, the two identities that we found earlier, divided the whole thing by cos a, cos b, and the tan identity just pops out. So final step now. So we've got tan a multiplied by 1, so that's just tan a. Sine b over cos b is tan b. Okay. And then cos b over cos b is just 1. And then subtract tan a and tan b, which is what we wanted.